Banu, please mute yourself.
పర్సనల్ బలహీనత ఎవరైతుందో కొద్దిగా బలహీనతలు ఎఫెక్ట్ అవుతాయి.
Very good afternoon, guys. We can start our today's session. Right now, we're in the week 3 of the Introduction to Material Science and Engineering course. Let's see the list of the content that we have covered. So in this week, we talk majorly on the closed pack structure. We talk about their voids. We talk under what condition they can make a what we can say. Just okay. Abhishek Kumar. And after that, we discuss about the Yumi-Rodri rule, where we discuss that okay under what condition a particular two elements is going to dissolve. For example, we talk about the copper and zinc, and we said that okay, zinc will dissolve into the copper to a certain extent. It's not going to dissolve to a very large extent, right? And then after that, we talk about the order and disorder in the solid solution. Under what condition ordering can be occur and disordering. Here we talk about the brass, where we took that okay, less than the 50 per uh, below 460 degrees Celsius. We saw that okay, there is a orderedness is there, but above the temperature, the the structure is converting to the disorder, and that is leading to the formation of the body-centered cubic structure, BCC. Then after that, our study was majorly on the graphene and the diamond. So this is at the end of the week we started the studying about the structure of the few standard materials. Okay. So I would like to ask you that this content which has been covered, is there any doubt in that? If there is, please you can write it in the comment box. If not, we'll move toward the solving the questions, which will help you in solving the assignment question. Okay. Since there is no doubt, let's go to the question number 1. So all the questions are quite easy and it's similar to the questions which has been asked in the assignments. The first question here is that in a closed pack structure, octahedral void are formed by how many atoms? Okay, so we need to we need to form the octahedral void. So what do you think? How many atoms will be needed to form the octahedral void? A, B, C or D? Like 4, 5, 6 or 8? So you've studied that we have a square pyramid and on top we can place an atom and on the bottom also we can place an atom and with that we can form this void. So what overall we need 4 atoms which will sit at the square lattice and then one top and the bottom, so total of 6. And for the tetrahedral void, instead of octahedral, if I would have asked for the tetrahedral, we know that it's formed by the pyramid 4. It will need total of the 4 atoms at 4 corners. So with that, in this question we can say that the right answer is option C. If there is any doubt, let me know, or else let's move to the next question. So, in this question, what is the approximate size of the largest sphere that can fit into the tetrahedral void without disturbing the surrounding atom? So, this calculation, this exercise we have done in the class. So, what is the result? What we have got? Like we are keeping a tetrahedral. It's a tetrahedron, and on top, so we form this void. At the center there is a void, but we have to make sure that this void should not disturb the atom at the corner. What is the maximum size it can have? From our calculation, we have got to know that it's 0.225 times r. R is the radius of the atom which is sitting over here, right? Okay, so with that we got that for the tetrahedral void it's 0.225, while for the octahedral void it will be 0.414. Just a minute, guys. Neeraj sir. Yeah, please pardon me. So we got to know that 0.225 is for the tetrahedral void. Like it will not disturb if we put any atoms which is of less than or equal to of this particular size, then it's not going to disturb our lattice. While if we keep more than that, then our lattice will be distorted. That tetrahedral void, it will distort the atom nearby to it. While for the octahedral, it's comparatively higher. So 0.414 r, where r is again the radius of the atom. So this is for the octahedral. And that's how we have solved this question. You guys can always answer the, if you if you are able to find the answer, you can always put it in the comment box. That is text. Okay, let's move to the next question if there is no doubt. Yeah. So this is quite interesting. Like you are investigating an unknown alloy. We are not aware that which one it is. You find that the solute atoms are significantly smaller and fit into the void between the solvent atom. Okay. Let us say my solvent is iron, which is made up of what we can say only the iron atoms sitting at the FCC lattice. Now, what kind of the solid solution it is? It will form. Like there is this atom which is very small, and it can fit into the void. So, if it can fit into the void among the solid solution, interstitial, phase separation, or intermetallic, which one it will be? What do you think? Yeah, that's Rami Reddy has told that it's option B. That's right. So it will go to the interstitial side, that is this the void, or solid, we can say tetrahedral or octahedral. It can occupy any of the side depending upon its size. So since it is not substituting, it's not replacing any of the atom from its lattice position. It's only taking the void size, void space. So it is going to take the interstitial position. So we can say that the option B is the right answer. Okay, let's move to the next question. It's a fill in the blanks type. Let's do it one by one. I'll hide it. Yeah. So austenite is an dash solid solution of a carbon in the gamma iron. So we just talk about the interstitial solid solution and substitution. Yeah, Abhishek, that's right. It's an interstitial. And we know that in the gamma iron, which is FCC, since it is going to occupy the interstitial solid, it is going to form the interstitial solid solution. So we know the carbon is also going to sit at the octahedral side. It's not going to occupy the tetrahedral. Okay. So on the void, among the voids also we are make sure that okay it's going to occupy the octahedral. What about the second one? Carbon atom in the austenite occupy a void in the crystal structure. Occupy dash void. That's what I talked about right now. So what do you think? Which void it will occupy? It's tetrahedral or octahedral, right? So it's going to occupy the octahedral void. Yeah, that's right. The maximum solubility of carbon in the gamma iron is approximately how much percent? So we, as per the phase diagram, we have known that max to max, since carbon is the one, carbon in the iron is an interstitial solid solution. It's, and we know interstitial solid solution are always going to put some strain onto the material. So, so the 100% solubility is not possible, not even the geometrically. And even when we take into account the strain factor, that solubility limit goes even lower. And so we can say that as per the phase diagram, we have got to know that only 2 weight percent it will occupy, right? So that is the maximum solubility of carbon in the gamma iron. Now let's go to the next one. Copper and nickel form the dash solid solution without any solubility limit. So now which solid solution it is going to form? Copper and nickel. Whether it will be substitutional solid solution or interstitial solid solution. That's right, Ramiredi. So here we can say that it will going to form the substitutional solid solution. So from this we can say that nickel can occupy, we can put as number of nickel in the copper, right? 10 weight percent, 20 weight percent to the even 100. So with that we can say that it's going to be it will form a substitution solid solution and without any solubility limit. Okay. So now let's the last one. The lattice structure of the alpha brass is dash while the structure is that. So alpha brass we know. Alpha brass is the one where we are going to keep the copper and zinc are there in the brass. Here, in this case, alpha brass, copper is 70% and zinc is 30%. Again, I am talking about the weight percent. Since I am putting that, we know that it's going to form the substitutional solid solution. So the crystal structure which they will occupy will be the lattice which they will form will be of the copper, FCC, FCC lattice, while the crystal structure is cubic close pack, right? So with that we can say that it's going to be from the FCC with the CCP lattice, CCP structure. So with that we have solved all this question. In this question number 4, like there were multiple question of total number of 5. So if there is any doubt in any of them, please let me know. Okay, since there is no, let's move. Yeah. Which of the following is an example of substitution solid solution? So among this, we have to select carbon in the gamma iron, copper in the nickel, zinc in the copper, or B and C. Yeah, that's answer D, right? B and C both are correct. Very good. Let's move ahead. While the carbon in the gamma iron is the interstitial, while these are the substitution. Yeah. So which of the following statement is correct regarding the solubility limit of the solid solution? We are talking about the solubility limit. All solid solution have a upper solubility limit. The word is that all solid solution. So first one will be the false, right? Because we know that there are the certain solid solution which don't have any limit. There is no limit onto that. They can dissolve as much as they want. Okay. So this is incorrect. Some solid solution have the solubility limit while other do not. Yeah, this can be the right one, right? Some of them are having the solubility limit. While some, for example, we saw that in the copper and zinc, they have certain solubility limit. Okay. While other do not, like some have solubility limit while other do not. For example, copper and nickel. If more examples we need, then we can say that the gold and silver is also the one example where they dissolve, there is no solubility limit to that. and then silicon and germanium is also there. So these are the list of the system where there is no solubility limit. And so with that, B is the right term. It's still, let's go ahead and see what are the remaining things. Carbon in the gamma iron has no solubility limit. We know it has solubility limit. It can only dissolve till 2 8%, max to max. So this is incorrect. A is incorrect. Copper and zinc have no solubility limit. No, we know that they are having solubility limit. So this is also incorrect. Copper and nickel have no solubility limit. So option C is also the correct. Sorry, E. So among this, we can say that B and E are the right one. Then with that, we have solved this question. If there is any doubt, please let me know. If not, we'll move ahead. Yeah. So I want you guys to answer this question. The question is telling that in austenite, that is gamma iron, carbon occupy which type of void? The type of void that carbon is going to occupy, whether it is a tetra, octa, or no, it's the substitutional sites or the edge void. What do you think? A, B, C. Oh, that's right. Octahedral void. Uh, Rami Redira. That's right. So for 7, we can say option B is the right answer. Let's move ahead. This one is also like very easy. So according to the Yumi-Rodri rule, for complete solubility, the atomic size difference between the solute and the solvent should be less than, option B is the right answer, right? Yeah, that's right. Perfect. So again, we can say that the 15% is the one. If we go above that, they are not going to form the solid solution. Like they will have some solubility limit. They will form solid solution. They will, but it's that they will have some solubility limit and they cannot exceed that limit. Again, there are some exceptions, but we are not going to discuss them. Yeah, here. No. Which type of solid solution is more likely to exhibit an upper solubility limit due to the geometric constraint? So solid solution we have heard, it can be the interstitial, it can be substitutional. Now, which of them they are telling that they will have solubility limit, but it's due to the geometrical constraint? Substitutional, interstitial, or both of them, or none of them? What do you think? For the substitutional, yeah, that's right. Option B is the right answer, right? Interstitial solid solution. For substitutional, we know since they will be having, as per the Yumi-Rodri rule, we have discussed that their size difference will not be much, less than 15%. So geometrical constraint will not be there onto it. And also other factor like electronegativity, I know those are already there, but we are talking about the geometric constraint right now. Let's focus on the size. So the size are approximately similar, but while in the case of interstitial solid solution, the size will differ. And for example, the carbon, the void of the maximum void which is present in the iron octahedral one, even if we are talking about the octahedral void, that void itself is a smaller compared to the size of the carbon atom. So if one carbon is going to sit onto that, they are going to produce the strain. Geometrical constraint will be there onto it, and that's the reason why in majority of the cases interstitial solid solution have this, due to this geometrical constraint, they don't show sorry, they have the solubility limit. They do not show the like 100% solubility, and this is the reason. Okay, so with that we have solved the 9 questions till now. Let's move ahead. It's a math pair, so everyone should answer. Let me one two. What do you think about the fourth one, Yumi-Rodri rule? Yumi-Rodri rule with fit with of them, A, B, C, D, or E. Abhishek is telling that it's C. Criteria for the solubility limit. That's right. So 3 is going to with C. Sorry, 4 is with C. And carbon in iron. Carbon in iron will be which one? Complete solubility? No. Interstitial solid solution? Right? So we can say that carbon in the iron is the interstitial solid solution, so it will match with D. So 2 is going to match with D. Now, zinc in copper. What about the zinc in copper? So zinc in copper will be, it will have some solubility limit or not? Yeah, that's right. It will have some solubility limits. So yeah. So Rami Reddy has told that okay, the third one is going to match with the A. Copper and nickel. Copper and nickel will have E, right? Yeah, that's right. Perfect. It will have a complete solubility. Now we are only left with the fifth one, octahedral void. It's and we are only left with B also, so it's a location of the interstitial solute. So we can say that it will match with the B. So our right answer is that E, D, A, C, and B. If any doubt, guys, let me know. Again, this question is having the multiple question within it. We'll do it one by one. It's a true and false type. So the first one is telling that Yumi-Rodi rule are strict law that all solid solution must follow. What do you think on this? Like they are telling that all solid solution must follow Yumi-Rodi rule. In the class we have, yeah, that's right. It's a false. In the class we heard that we discussed, we learned that okay, Yumi-Rodi rule is just an experimental rule, empirical rule. It's some system can obey it, but there are a lot of exceptions also are there which are not going to obey this particular law, and so with that we can say that it will be false. Now second one, interstitial solid solution can exhibit unlimited solubility. Example, you can think whenever they say interstitial solid solution, you can always think in your mind, okay, carbon in the iron, in the gamma iron. What do you think, whether it will be true or false? Again, it's a false, right? Perfect. Now copper and nickel form a system with a complex solid solubility, with a complete solid solubility. Copper and nickel form a system with a complete solubility. So we have studied that copper and nickel are the system where they are following all the four Yumi-Rodi rule. That is crystal structure. They both of them are having the FCC. Their sizes are within the less than the 15%. Electronegativity and are very close with each other, and the valency is also very close. And so we can say that it will be true. Now D. The crystal structure of solute and solvent must be different for complete solubility. They are talking about the complete solubility, but they are telling that okay, it should be different, which like the crystal structure should be different. No, they in majority of the cases it should be same, right? Sorry, it should be same. Yeah, that's right. So Abhishek and Reddy. Yeah, perfect. So both of you told that it's a false. Now the final one. A size difference of more than 15% between the solute and the solvent atom decrease the likelihood of complete solid solubility. So what is your comment on it? True, perfect. Right. So among all this, only C and the E were the two which were true. Remaining three are false. So with that, question number 11 is over. If you find any difficulty, you can let me know. Now these are the things which we have learned in the class. All we have to do, we have to match with their crystal structure. What do you think for the alpha brass? Alpha brass we talk about. Let me write first. 1, 2, 3, and 4. Alpha brass we talk about. Okay, it will be the copper and zinc. They are following. Yeah, it's a B FCC. Yeah, that's right. Right. Here zinc is 30 and the copper is 70%. And we know that since they are forming that solid solution, So it should take one of the structure from the one of the structure, either copper or zinc. And we know that okay, copper is in the majority here, so it should follow the structure of the copper. So we can say that okay, since copper has the FCC, so it will be having FCC. Now for about the beta brass. So among the beta brass also, so first one is going is matched with B. In beta brass, there are the two structures. One is above the 460 and one is below the 460. The one which is below the 460, let's draw that. Meanwhile, if you know any of this, second is matched with the C. Abhishek is telling that. So second one is going to match with the BCC crystal structure. That's right, perfect. And so the third one is going to match with. You can also write the answer for the third one. Third one is going to match with the D. That's right. Right. So let's discuss little bit this beta brass. That's right. So we can say that at less than 460 temperature, since copper and zinc are there, copper will occupy all the corners, or zinc will occupy all the corners. Anything you can say. And then the another one, let us say this is a copper, so we can say this one, this blue one, will be the zinc. It's going to occupy the middle portion, right? So it is below 460, and we cannot say that this is a body centered just because the atom is at the body centered. The reason is that the atom at the lattice point of the corners and the one at the center are different from each other, and so we cannot say that okay, there will be BCC. The structure of CSCl, this type of structure has given the name of CSCl, so we'll match with that. While if we increase the temperature, the probability that okay, the copper will occupy this particular corner sides and the zinc will occupy this corner side is 50-50%, right? And so for the center one also, so all of them are equivalent with each other. So all the lattice point, even the body centered one and the corner one, they are equivalent from each other. So statistically they are BCC, and that's how we have matched it. So with that, B and C is over. Sorry, 1 2 3 is over. Now copper nickel solid solution, what do you think? Copper and nickel, which one will be? uh, Fourth one is going to match with what? See, I just put the SCP, but it is not the right answer. I just put it just for the confusion, just to create a little confusion in us. We just discussed that copper and nickel solid solution, they are going to form the complete solubility, right? Copper is FCC, nickel is also FCC. So the fourth one is also going to match with the B. So the first one, the right answer is okay. The overall answer, if we write, it will be the B, then C, then D, and then again it's a B. A is just a redundant, just to create a little bit of confusion. I hope it's clear. If there is any doubt, let me know. Since if there is not, we'll move ahead. Now again, it's a true and false type. So the first part, the graphene has the three-dimensional crystal structure. Now, what is your comment on this? A is false, right? That's right. So Abhishek told that it's false, and we know that graphene is a 2D lattice. It's not going to. It's just along the two dimensions. It's not the 3 dimension. A unit cell of the graphene is a square. Now, what do you think? Is it a square? Yeah, that Reddy has told that it's false again. So what is the unit cell if we talk about? It's not the square. We got to know that okay, it's not the square. Then what it will be? So it's a hexagon, right? So the right answer of here, if I have to make it true, it should be the hexagon instead of the square. So the Nobel Prize for the graphene was awarded in 2010. It's just a factual question, so it's a true. We'll not discuss it. Yeah, that's right. Oh, it's good that factual things also we are able to remember. Graphene is a single layer of graphite. What do you think? That's also true. Yeah, that's perfect. So with that, we have solved this. It's a single layer of graphite, and that's how the graphene has discovered. Okay, people were just taking the graphite tape, putting on to the one of the sheet, and just removing it. So what happened that the one layer of the graphene got stuck to it, and that's how the from the graphite one has produced the graphene. Let's move ahead to the next one. Again, this question is very easy. What is the stacking sequence of the graphite layer? Remember, we are talking about the graphite. Yeah, that's right. Option C is the right answer. So they are not like one layer of. If I want to build a graphite from the graphene, let us say, from the bottom up approach, let me tell you, people don't do that. Graphite is a very cheap and naturally available. But hypothetically, let us say that I want to build a graphite from the graphene. Then it's not be like, okay, I took the one layer of graphite, so one layer of graphene, and on that layer itself I am stacking in the one above the another. They are shifted, and they are shifted by the amount of lattice parameter A, and that's the reason why we are calling it to be the AB stacking, not the AA stacking. While ABC stacking, we know that it's usually been followed in the FCC, right? And there is no stacking like this. With that, we have solved this. Yeah, AA stacking is in the simple cubic. Okay, guys, let's move ahead to the next question. Huh. So, how many atoms are present in a unit cell of the graphite? 2, 4, 6, or 8? It's a little interesting. Let's okay, since there is some confusion, we'll draw it. Actually, this was the part which professor left for us to do the homework. Like, he told that okay, we can find it. And one carbon atom is somewhere over here. Now there is a B layer. On B layer, it's occupying the edge, and it is occupying just above this, like not above this one, this particular point. So it will somewhere over here. So they are in the one layer. Now the third layer, the above one, will follow as it is, the one which we draw at the bottom one. It will be over here. Since we made the structure, now we can solve it. See, let's talk about the bottom one. We know that this point, these corners are going to contribute 1 by 8 toward the lattice. We can multiply, okay, how many are there? A total of 4 are there. Now this atom, it is sitting at the face. So we know that it's going to contribute only the half, and the only one of them is there. The pattern which this bottom one will follow, the same will be followed by the top one. So we can multiply it by 2. Now we are left with this particular, the middle one. So A layer is over, B layer is over, and there's A layer is again over. Now for the middle one, we know that they are sitting at the edge, not at the corner. So edge is going to contribute by 1 by 4. How many are there? There are total of 4. 3 and 4. And then there is 1, which is somewhere over here. And this is going to contribute entirely 1, because it is inside the unit cell. Now let's calculate it. It will be 1 by 2 plus 1 by 2 plus this is 1 and this is 1. So we can say 2 multiplied by this half and half is 1, and this is 2. So overall we can say there are the 4 atoms. So in the graphite unit cell we can say there are total of the 4 atoms that is corresponding to. So one unit cell will have 4 atoms. There was one more structure FCC which was having the 4 lattice point correspondingly. Okay, so if there is any doubt in this, please let me know. There was one more task given by the professor that we have to find the coordinate of these particular atoms, which is very easy. uh, I leave it to you. If you find any problem in that, we can discuss it. Okay, since there is no doubt in this question, let's move ahead. Okay, so guys, please answer this question 16. So in a daily basis we know that okay, graphite is used as a lubricant, and what is the reason for that? See, among the layer, yeah, that's right. Option C is the right answer. Uh, just like Reddy has told that option B is the right. And what is the reason that? The reason is that among the layer, the bonds are very tight, like they are very strong. The covalent bonds are very strong. But between the layer, the bonds are the van der Waal, and those are weak. Van der Waal bonds, since they are weak, they are easy to break. So once we apply some little bit of force to it, one layer can slide on top of the another layer, and that's the reason why it is used as a good lubricant. Okay, so with that we have solved this. Match the pair, column A and column B. Here we are having the graphene. What do you think? A will match with what? Which of them? 2, 3, and 4. So Reddy is telling that it's C. That's right. That's right. It's a two dimension. It's a 2D structure. What about the second? The graphite. A, B, or D? So we know that graphite will follow which type of stacking? It will follow the AB stacking, right? So that's how we can say that it's option D is the right answer. So van der Waal bond, third one will match with the option A. Sorry, option B, weak interlayer force. And the carbon fiber, we know they are strong within the layer direction. So with that we can match it with the option A. Okay, and that's how we have solved it. Now this is little interesting. You will find that in the assignments, the last question, the question number 10, will be somewhat based on this. And this thing, again, it's been done in the class. We have to draw the projection representing the ordered beta brass, and also write its correspondingly lattice and motif. Since we are talking about the ordered, that is, so we know that since we are talking about the ordered beta brass, first of all it's a brass, so it's a copper and zinc. And since it's a beta brass, so we can say that it is 50-50%. Now let's draw its crystal structure. We have already did it, but to draw the projection, we have to do like that. So here it's a copper, let us say the black one is copper, and the blue one is a zinc. Now we need to draw its projection. Let us say we are drawing the projection onto this particular plane. That is XY plane. This is X, and this is Y. So all the copper atoms, this one, it will sit at the corner. Since we are drawing the projection, so this top one will also be projected, but we know since they are just above each other, so we no need to draw anymore. They will they will project at the same position. Now, the only all these 8 atoms are over of the copper. Now we are only left with the zinc, and zinc, if we project it from the top, it will come over here, just in the middle. And we know as per the crystallographic convention, we have to represent all the fractional coordinates, that too along the c direction, not all of them, okay, not like b and a direction. We only have to represent about the c direction. So among in c direction, we know that this atom is at the location of a by 2. If entirely is a or entirely is c, so we can say it is at the c by 2. So 1 by 2, the fractional coordinate we will write. Okay. Now one can ask that why we are not writing the x and y. It's already been here, x and y. So we no need to write it any further. We the only the information which is hidden by this particular projection, the 2D projection, is the among the third direction, and that's what we have noted it down. So this is how you have to project. So in the assignment, you will see that uh, instructor has asked us to do for the diamond, and it won't be very tough. Okay, you can do it. If you face any difficulty in that, we can again discuss in the next class. By the way, any doubt in this? Okay, since there is no, let's move ahead. Huh. So, the option 19, like the question number 19, the additional atom in the diamond cubic structure are located at. Why additional? Diamond cubic, we know it is forming the FCC. Option C, yeah, that's right. So, Reddy has told that okay, it's a body diagonal at fractional position. In FCC, we know that they will occupy the face-centered lattice, but so there should be only 4 now. But we know in diamond cubic there are total of 8. So the remaining 4 are sitting at which location? So these are the along the body diagonal they are located, and they are located something about 1 by 4, 1 by 4 and 1 by 4. This location from the 0, 0, 0. Right. Okay, let's move ahead. Uh, we don't have any more questions, just 2 more are left. After that, we will wind up. So the lattice of the diamond cubic structure is, now we are not talking about the structure, crystal structure. We are talking about the lattice. What do you think? It's a FCC, right? Face-centered cubic. That's right. Perfect. Well, the crystal structure, if someone asks of the diamond, then it's a diamond cubic. It's simple, very diamond cubic. Okay. Okay, let me tell few things. Simple cubic, we know, like which metal is the one which will take the simple cubic? Polonium, right? Body centered, any idea which of the things that we have studied will take the body centered one? Like which metals can be the BCC? Iron, right? Yeah, iron is a good example. We can say the alpha iron, and delta iron is also there. Perfect. Hexagonal close pack. Which one will be the hexagonal close pack? So hexagonal close pack, we have studied that zinc is one of the good example, SCP. Okay. Okay, let's move ahead. Now, just 2 more questions are left. We'll complete them. So it will be very interesting. Please try to answer them. It's a match the pair. You guys write for the first one, diamond cubic structure. Abhishek is telling that the option E, FCC lattice plus motif. That's right. So diamond we know it's having the FCC lattice plus motive. Motive is made up of the yeah. So a motive is made up of the two carbon atoms. One is at the 0, 0, 0, another is at the 1/4, 1/4, 1/4. So these are the two coordinates which we are having. Sorry, these are the and also the carbon is the one. So for the motive, if we have to define, so the motive will be total of it should consider about the coordinates also, where the particular atoms are, and also it talk about the which atom. Like in some case, it might be possible that it's not the carbon, it can be something else. The additional atom can be something else. So now, this match the following is entirely for the diamond cubic structure. Okay. So now second one, what do you think? Atoms at the corner. How many atoms are there at the corner? Yeah. So Reddy has told that it's option D is the right answer. So the total of 8 atoms are there at the corner of the unit cell. Additional atoms, where are the additional atoms are sitting, which we have already talked about. So third one is going to match with the located at the body diagonal. It's going to match with the C. Face centered atom position. So now, how many atoms are there at this face center in the diamond cubic? So yeah, that's right. The answer is B. The fourth one is going to match with B. So the Miller indices of the body diagonal, we know that 1, 1, 1 it will be. So option A. And with that we have solved this question. So now the final question which is here. Here the match the pair we have to do in the three manner. So let's do for the number and the alphabets first. Diamond cubic. What is the coordination number of it? Let's say we are talking about the carbon. 12, 4, 6 or 8. What do you think? 4, right? Yeah, that's right. So it's going to match with the B. It's going to form the tetrahedron, and we know that tetrahedron is the one it's only having the 4 coordination number. So the option B is the right answer. Simple cubic. Simple cubic will have 12, 6 or 8. So 4 is already over. You can also consider 4, but it's up to you. Okay, yeah, that's right. It's going to have a 6. That is the option C is the right answer. For BCC, we know that the overall coordination number is 8. So it's going to match with the D. And the only one, the close pack. See, we can see that FCC, face centered cubic, the close pack structure. It's close pack because it's having this many coordination number. So the fourth one is going to match with the A. Now, let's talk about the packing efficiency. So the packing efficiency, if we talk for the diamond cubic, it will be which one? 0.334, right? So it's going to match with the 4. See, we just now discussed that diamond cubic is having the structure of FCC, right? But on top of that, it is also having some additional atoms at the body diagonals. Total of 4 additional. So one might be thinking that okay, since it's having more atoms than the FCC, it will have more packing fraction also, packing efficiency also. But which is not the truth. We can see that it's only 0.34. Okay, let's move ahead. For the simple cubic, which one it will be? It's a 0.52. That's right, perfect. So the third one is the right answer. This is over. BCC is a right. It will be only nothing but a 0.68. Perfect. So it will be second, and then FCC we all know that it will be the 0.74. So it will be the first one. And with that we have solved it. It's not very tough. It was very easy. So let me tell you, this question has been asked in the gate. Okay. I not remember which year it was, but it has been asked. Okay guys, so with that we have solved total of the 22 questions. Let's have a look on all of them. I will place it on one top of each other, and if you find any difficulty in that, please let me know. Also, The content that has been discussed in the class, if you have any doubt in that, that also you can discuss. We have till now we have solved the assignment 1 and 2, and I think we submitted both of them. And if you have any question to discuss among that assignment also, you can let me know. 21st was this. So this week content was quite easy, and lot of visualization was the one which was needed. Right now we are very fresh with the beta brass, but with time it will get fade away. Always try to remember that at lower temperature they will form the order, and the higher temperature they will form the disorder structure. These are the graphene. We talk about the structures. In upcoming weeks, we are again going to talk more about the structure, like CSCL. We'll take all the structure one by one. This is the graphite. And then we talk about the stacking of the graphite. Then few facts about the graphene. Then we talk about the order disorder, the brass, like which structure they are forming. The Yumi Rodri rule we discussed. And this is a question on that. And then we discuss about the solubility limits in various system, like the copper, nickel, zinc, and those things. Okay, we talk about the interstitial solid solution. We talk about the limitation of the Yumi-Rodri rule. Okay, sorry, not limitation. What Yumi-Rodri says that okay, 15% of the size difference should be there. If it is more than that, then they will not satisfy the rule. We talk about the void, tetrahedral and octahedral void, and which void carbon is going to occupy in the gamma iron. We talk about the limits, solubility limits in the various system, and then here again it's the same thing, whether it's the interstitial or the substitutional one. Yeah. So these are the couple of questions which we have discussed. So I made the question as per the class, like since we started first with the voids and close pack, so we discussed question like that. Then solid solubility, Yumi-Rodri rule we discussed, order and disorder, graphene, and then the structures. So you will find that all the questions are like that. One more thing, guys. So with that, this is over. Today's class is over. I have few announcement to make. You can go to the NPTEL site, and from there you can access this dot solving session video. There will be the one tab where you can click like the dot solving session is there. When you click, there will be the two options. The second one is the one which is form. So you can fill that form. You can let me know the feedback, how you are liking this session and all. So and what kind of improvement you want, what kind of questions you want to add. Like some of you might can be like, okay, we should discuss initially the assignment question, like the previous week assignment question. What are the difficulties you might have faced? Those things, any feedback you can write. Okay, it's up to you. So with that, I'm going to wind this session, and we'll meet again in the next week, same time, same on Saturday itself. Okay, guys. Bye.
Briefly.
Yeah, yeah. Please go ahead.
In previous assignment in week 2, there was question how to find into Miller indices.
Okay. Let me open that tab. Yeah. So I not attended any of the question last week. So here we can see that we are talking about the which question, Abhishek. Can you tell me the question number?
Question 5.
Question number five. Okay. Yeah. The acute angle between these two. That is what we need to find, right? Okay. Let's discuss that. Can you bring me few blank pages? Abhishek, apart from this, is there any other question, or shall I start explaining this?
No, sir.
That's the one, right? Okay. So it's 112 and 111. 1 bar 0. Okay, so these are the two directions of which we have to find. It's very easy, just a vector. We know that if we have two vector, let us say v1 and v2, how we can find them, what how to find the angle between them. So seventh question too. So okay, yeah, we'll discuss that. So we have to find the angle between these two vector v1 and v2. We are aware that if we do the dot product of them, v1 dot v2, it will be mod of v1 mod of v2 and cos of theta. So cos of theta is angle between them. We can find it that v1 dot v2 divided by mod of v1 mod of v2. All we have to do is we have to substitute these things. So v1 and v2 dot product of them. This is, let us say, v1 vector and this is v2 vector. We have to find the dot product. So 1 multiplied by 1 will be 1 plus 1 multiplied by 1 bar is nothing but minus 1. So we'll multiply with minus 1 plus 2 multiplied by 0. The whole divided by mod of v1, that is 1 square plus 1 square plus 2 square. And then we have to multiply this with the mod of v2, that is 1 square plus minus of 1 square and plus 0. So it's just the mathematics. This got 0, 1 and 1. This is 1 and this is, it will be minus 1. So we got to know that it's 0 only, right? So no matter what at the denominator, since it's a valid number something, so we don't have to concern about it, whatever it will be. So overall we got 0. So cos theta of 0 is nothing but the theta will be 90 degree. So these two directions should be what we can say, it should be perpendicular with each other. Let's see the answer. Where is my site? So the right answer is the 90, right? So that's how we have got it. Question number 5. So Abhishek, is it clear?
Yes, sir. Thank you. I
Yeah.
have done the calculation mistake.
Oh, yeah, it's happened. Like some silly mistake can happen. Okay. So now already is talking about that seventh question. Actually, I focused this particular question number 7, like to a large extent in the dot solving session. So let's discuss it. The question is telling that what are the Miller indices of the plane that make intercept of 1 angstrom, 2 angstrom, and 3 angstrom. Yeah, with A, B, and C axis respectively in the tetragonal crystal, with C by A ratio is 2. So C by A is 2. And again, the fact we know that it's a tetragonal. And we need to find what is the Miller indices of the plane that make this intercept. Okay. Yeah. So these are the content we know. I just noted it down. See, 1 angstrom, 4 angstrom, and 1, 2, and 3. They not focus. They not told any. They not give any information about A, B, and C, right? But we know that when we talk about the any when we want to write any Miller indices and all, what we do usually, like, are they talking about the plane now? Yeah, it's a plane only. So for the plane, we know that we have to write in terms of A, B, and C. So for example, let us say 1 angstrom, 2 angstrom, and 3 angstrom they are making. Let us say I am telling that my A, lattice parameter A, is nothing but 1 angstrom. So lattice parameter A is 1 angstrom. So we got so in that way, and we also know that for the tetragonal A is equal to B, which is not equal to C. Now let's write this: 1 angstrom, 2 angstrom, and 3. in terms of A, B, and C. So now I told that okay, A is 1 angstrom, so I can write this is 1A, this is 2A, right? So we can write it will be the 2 times of A. Now 3A, I can write it 3 times of A. I consider that 1 angstrom is a A. This is my lattice parameter. You can consider it to the 2 angstrom to be the A. It won't make any difference. We just have to follow these rules. Now again, I have to represent this first one with in terms of A, which is it's there. Second one I have to represent in terms of B, and I know that A is equal to B. So I will write 2 of B. Now third one I have to represent in terms of the C. It is given that C by A is equal to 2. So what can I do? So I will substitute A will be equal to the C by 2. So I will write 3 C by 2. So now from here I can take 1, 2 and 3 by 2. Right. What is the next step I have to follow? Here I have to take the reciprocal of them. In the plane we take the reciprocal. So what I will do, when I reciprocate them, better I write here. When I reciprocate them, it will be 1 over 1, 1 over 2 and 3 over 2. Now what we have to do, we have to take the common multiple, right? We have to normalize it. We have to make it in the single integer. So sorry, it will be 2 by 3. So with what we will multiply? We will multiply 2 and 3 is a common factor. We can say that like multiple of this will be 6. So we'll multiply entire thing by 6. So it will be 6. It will be 3, and this one will get 2. So 6, 3 and 2. This is the plane which is of our interest. Okay, it will be multiplied with 6 now. So it will be multiplied with, it will cancel. So 6, 3 and 4 is the right answer. Let's see the answer. Yeah, it's 6, 3 and 4. Option A is the right answer over here. Okay, so ready, is it clear, this one? All we did is, yeah, that's great. All we did here is we have to represent this thing in terms of A, B and C. See, one can make a mistake. They will directly take what students usually do. They will take this 1, 2 and 3, and this with this 1, 2 and 3 they follow this step. And that's why they directly reciprocate this and they directly do this, which is not the case. For the Miller indices, for the plane, we know that we have to represent in terms of A, B and C only, and then only we can proceed. Okay, so people usually miss these steps. Again, so let me tell you that I was talking about this dot solving session, right? So you can access this. These are the session which I took. You will see that okay, there are the 2 sessions already over, and I will also upload the PPT as mentioned over here. Okay, I forgot to upload week 2. I'll do that. And then again, this thing here, you can see the survey. You can click on this form and you can submit this particular thing, like your name and all, whatever you like to, and then after that you can rate this. If any feedback, anything you want to write, if you want me to know, please you can do it over here. I will put this in the comment box. Okay guys, if there is any doubt, let me know. If not, then we can wind up the session. Okay guys, with that week 3 also, week 3 I not got, yes, see, for the week 3 the assignment we have to submit, like, so I cannot solve exact these questions. Week 3 assignment is also discussed. No, we discussed the list of the questions which is as similar as the week 2. If you see my week 3 assignment, if you see my week 2 dot solving session, you will find that okay, those questions has been discussed which is similar to the assignment of the week 2. So we do like that. I'm not allowed to discuss this question as it is. But you can see that okay, I discuss about that CSCL structure, which are something remember with this. So this list of the question which we have solved today. Okay. So you can go through this. You can submit this assignment. You can submit as many times as you want. Your final assignment is the one. The final submission is the one which will be considered. Again, we'll discuss this week 3 assignment if you face any problem in the next upcoming week, week 4. Okay. Make sure that you go through the week 4 content and also solve these questions. Okay, guys. Okay, yes, great. Okay. Ram Reddy, yes, and Abhishek, everyone, yeah. So with that, we can conclude our today's session, since there is no any further question. Okay, guys. Bye bye.